Welcome back to The Explainer, where we take complex, really fascinating ideas and break them down for you. Today, we're going on an absolutely incredible journey. We're going to start at the macro scale, the everyday objects you can see and touch. Then, we're going to shrink way down into the microscopic depths of nanotechnology, where we're literally manipulating the fundamental building blocks of the universe. And finally, we'll zoom back out to see how those tiny, invisible changes are going to radically transform our entire world.
Okay, let's dive into this. As MIT's Professor Jeff Grossman so perfectly put it, we live in the age of atomic design. For basically all of human history, we defined our eras by the bulk materials we just, pulled from the ground. Think about it. The Stone Age, the Bronze Age, the Iron Age, the Age of Plastics. But we're never going to do that again. We are now actually realizing the great physicist Richard Feynman's dream. We have the ability to put atoms exactly where we want them. So it's really no longer a question of can we make it, but rather what should we make?
So here's our roadmap for today. We'll kick things off with the age of atomic design, look at the building blocks of matter, and then explore designing molecular machines, clean energy catalysts, smart infrastructure, and finally, wrap up with our nanotech future.
Let's start with Section 1, the age of atomic design, and what it actually means to move beyond bulk materials. Historically, our relationship with materials has been, honestly, a bit brute force. We dig stuff up, we melt it down, and we hammer it into shape. But atomic engineering? That's a completely different paradigm.
Now what's really interesting here is the number 63. If you grab the smartphone sitting in your pocket right now, it doesn't just contain a couple of basic materials. It actually relies on 63 perfectly orchestrated elements from the periodic table, all working together in harmony just to turn on your screen and connect you to the internet. We have truly moved out of the silicon age and into a full-blown chemistry revolution.
And you know why this matters becomes wildly clear when we look at how we currently use resources. Let's take a standard barrel of oil. Today, we mostly just burn it. If you burn all 159 liters of that oil, you get about 1.73 megawatt-hours of energy. But with atomic design, if you take just 1% of the carbon in that exact same barrel of oil and instead arrange those atoms into a thin-film graphene solar cell, it yields 10,000 times more energy over a year than just setting it on fire. Nanoscale design unlocks this revolutionary, almost mind-boggling level of efficiency.
Which brings us to our second section, the building blocks. To truly grasp this revolution, we really need to shrink down, way down. Long before modern chemistry was a thing, ancient thinkers like Democritus proposed that if you kept cutting an object in half, eventually you'd reach a piece so small it was indivisible. He called these atoms.
Just to ground us firmly for a second, let's define our physical world before we rebuild it. Matter is simply anything that has mass and occupies space. And at its most fundamental level, absolutely all of it is composed of these tiny spherical building blocks we call atoms. Whether it's the screen you're looking at right now, the air you're breathing, or the neurons firing in your brain, it's all just made of atoms.
But here's a truly surprising fact: the immense, infinite complexity of our entire universe. It's built using a palette of just 118 known types of atoms. That is it. Just 118 fundamental Lego bricks that combine in endless, crazy variations to construct literally everything that exists.
And that brings us right to the core of this explainer, nanotechnology. Simply put, nanotechnology involves the manipulation of matter on a molecular and atomic scale, typically somewhere between 1 and 100 nanometers. When you get down this small, the normal rules of physics fundamentally change, which gives materials entirely new superpowers. And this is paving the way for some unbelievable future inventions. We're talking about nanomachines that can actually repair damaged tissues and organs from the inside out, nanofilters that can flawlessly purify our water and air, and nanoscale materials that can completely revolutionize energy storage and generation.
All right, stepping into Section 3, designing molecular machines. If you were to look at a living cell under a super powerful microscope, you'd see it isn't just a boring blob of jelly. It operates like this ginormous, bustling city, complete with microscopic factories processing incredibly complex chemistry. And the workers inside those factories? Those are proteins.
Let's see how this builds, because this biological city is getting a massive upgrade right now thanks to artificial intelligence. For 60 years, figuring out the 3D structure of a protein, how that long, messy chain of amino acids folds up into a functional shape, was this monumental mystery. It was basically the Fermat's last theorem of biology. But recently, an AI called AlphaFold completely solved it. By mapping these structures, we've gone from just passively observing nature to actively programming it.
So the crucial point here is that mapping these structures launched a whole new era of synthetic protein design, stuff that now happens in days instead of decades. We are literally building tiny molecular nanomachines to solve massive global crises. We're talking synthesizing human-compatible antivenoms for lethal snake bites that you can manufacture anywhere. We are running clinical trials for cancer vaccines. We're even designing custom enzymes that act as biocatalysts to capture greenhouse gases and actually digest and break down the plastic waste that's choking our oceans.
Let's pivot to Section 4, nanocatalysts and clean energy. We've seen what atomic manipulation does for biology, right? Now let's look at how it allows us to capture sunlight, generate clean fuels, and safely break down environmental pollutants using nanoscale catalysts.
It's a process called visible light photocatalysts. Essentially, a nanoscale material absorbs a photon of sunlight, which generates an excited electron. Now, in regular bulk materials, these excited electrons act kind of like teenagers at a middle school dance. They immediately rush back together and recombine before any useful chemistry can happen, and the energy is just wasted as heat. But by using nanoscale engineering, we create these tiny physical hurdles. We keep those charges separated just long enough to transfer them to the surface where they can do incredible work, like splitting water to create clean hydrogen fuel or converting CO2 into really useful chemical building blocks.
All right, Section 5, Smart Materials and Infrastructure. Let's zoom all the way back out to the macro scale. How do we take these unseen, microscopic chemical miracles and apply them to the physical cities, roads, and buildings we interact with every single day?
And this brilliantly illustrates the solution, an incredible hybrid. By embedding highly conductive, super flexible, superconducting organic polymers with advanced nanoparticles, we can stop treating concrete and steel like they're just dumb heavy weight. Instead, we're creating intelligent infrastructure, stuff that can actively think, sense stress, harvest solar energy, and instantly respond to environmental changes.
To ground this in reality, let's look at some real applications. If we mix titanium dioxide nanoparticles into building facades, we create walls that are photocatalytic, meaning they literally use sunlight to eat smog and clean the air around them. If we add carbon nanotubes, we get this incredible mechanical strength and electrical conductivity in super lightweight materials. And if we embed special microcapsules, we get concrete that can sense a crack forming and uses capillary action to bleed a healing agent, physically repairing itself before the structure ever fails. How cool is that?
And finally, Section 6, our nanotech future. Ultimately, manipulating atoms is the grand bridge between repairing human health and restoring the environmental sustainability of our planet. It really is the ultimate toolkit.
And this matters because nano-encapsulation fundamentally changes the way we heal. When we use biopolymer nanoparticles made from completely natural materials, things like chitosan or lignin, we can create microscopic delivery vehicles. We can encapsulate super fragile medicines or natural plant-based agricultural protectors, shielding them completely until they reach their exact target. This perfectly delivers the payload right to the disease cell or the specific crop pest, and it entirely bypasses the toxic side effects that come from just flooding our bodies or our soils with bulk chemicals.
We've really crossed a threshold here. We aren't just consumers of whatever materials nature happened to leave lying around anymore. We are the architects of the microscopic world. So I want to leave you with this thought to ponder. As this technology matures, and if you had the power to put atoms absolutely anywhere you wanted, what would you choose to build?